an elementary course in Synthetic Projective Geometry by Derek Norman Lehmer. Chapter 7, Metrical Properties of the Conic Sections. Section 107, Diameters, Center. Section 108, Various Theorems. Section 109, Conjugate Diameters. Section 110, Classification of Conics. Section 111, Asymptotes. Section 112, Various Theorems. Section 113, Theorems concerning asymptotes. Section 114, Asymptotes and Conjugate Diameters. Section 115, Segments cut off on a chord by hyperbola and its asymptotes. Section 116, Application of the theorem. Section 117, Triangle formed by the two asymptotes and a tangent. Section 118, Equation of hyperbola referred to the asymptotes. Section 107, Diameters, Center. After what has been said in the last chapter, one would naturally expect to get at the metrical properties of the conic section by the introduction of the infinite elements in the plane. Entering into the theory of poles and polars with these elements, we have the following definitions. The polar line of an infinitely distant point is called a diameter, and the pole of the infinitely distant line is called the center of the conic. Section 108. From the harmonic properties of poles and polars, the center bisects all chords through it. Section 39. Every diameter passes through the center. All chords through the same point at infinity, that is, each set of parallel chords, are bisected by the diameter, which is the polar of that infinitely distant point. Section 109, Conjugate Diameters. We have already defined conjugate lines as lines which pass each through the pole of the other. Section 100. Any diameter bisects all chords parallel to its conjugate. The tangents at the extremities of any diameter are parallel and parallel to the conjugate diameter. Diameters parallel to the sides of an inscribed parallelogram are conjugate. All these theorems are easy exercises for the student. Section 110, Classification of Conics. Conics are classified according to their relation to the infinitely distant line. If a conic has 2 points in common with the line at infinity, it is called a hyperbola. If it has no points in common with the infinitely distant line, it is called an ellipse. If it is tangent to the line at infinity, it is called a parabola. Section 111. In a hyperbola, the center is outside the curve. Section 101. Since the two tangents to the curve at the points where it meets the line at infinity determine by their intersection the center. As previously noted, these two tangents are called the asymptotes of the curve. The ellipse and the parabola have no asymptotes. Section 112. The center of the parabola is at infinity, and therefore all its diameters are parallel, for the pole of a tangent line is the point of contact. The locus of the middle points of a series of parallel chords in a parabola is a diameter, and the direction of the line of centers is the same for all series of parallel chords. The center of an ellipse is within the curve. Section 113, Theorems concerning asymptotes. We derive as a consequence of the theorem of Briançon, section 89, the proposition that if a triangle be circumscribed about a conic, the lines joining the vertices to the points of contact of the opposite sides all meet in a point. Take now, for two of the tangents, the asymptotes of a hyperbola, and let any third tangent cut them in A and B, figure 28. If then O is the intersection of the asymptotes, and therefore the center of the curve, then the triangle OAB is circumscribed about the curve. By the theorem just quoted, the line through A parallel to OB, the line through B parallel to OA, and the line OP through the point of contact of the tangent AB all meet in a point C. But OACB is a parallelogram, and PA is equal to PB. Therefore, the asymptotes cut off on each tangent a segment which is bisected by the point of contact. Section 114. If we draw a line OQ parallel to AB, then OP and OQ are conjugate diameters. Since OQ is parallel to the tangent at the point where OP meets the curve, then since APB and the point at infinity on AB are four harmonic points, we have the theorem: conjugate diameters of the hyperbola are harmonic conjugates with respect to the asymptotes. Section 115. The chord A double prime B double prime parallel to the diameter OQ is bisected at P prime by the conjugate diameter OP. If the chord A double prime B double prime meet the asymptotes at A prime B prime, then A prime P prime B prime and the point at infinity are four harmonic points, and therefore P prime is the middle point of A prime B prime. Therefore, A prime A double prime is equal to B prime B double prime, and we have the theorem: the segments cut off on any chord between the hyperbola and its asymptotes are equal. Section 116. This theorem furnishes a ready means of constructing the hyperbola by points when a point on the curve and the two asymptotes are given. Section 117. For the circumscribed quadrilateral, Briançon's theorem gave, section 88, the lines joining opposite vertices and the lines joining opposite points of contact are four lines meeting in a point. Take now for two of the tangents the asymptotes, and let AB and CD be any other two, figure 29. If B and D are opposite vertices, and also A and C, then AC and BD are parallel, and parallel to PQ, the line joining the points of contact of AB and CD, for these are three of the four lines of the theorem just quoted. The fourth is the line at infinity, which joins the point of contact of the asymptotes. It is thus seen that the triangles ABC and ADC are equivalent, and therefore the triangles AOB and COD are also. The tangent AB may be fixed, and the tangent CD chosen arbitrarily. Therefore, the triangle formed by any tangent to the hyperbola and the two asymptotes is of constant area. Section 118. Equation of hyperbola referred to the asymptotes. Draw through the point of contact P of the tangent AB two lines, one parallel to one asymptote and the other parallel to the other. One of these lines meets OB at a distance y from O. The other meets OA at a distance x from O. Then, since P is the middle point of AB, x is 1/2 of OA and y is 1/2 of OB. The area of the parallelogram whose adjacent sides are x and y is 1/2 the area of the triangle AOB, and therefore, by the preceding paragraph, is constant. This area is equal to xy times the sine of alpha, where alpha is the constant angle between the asymptotes. It follows that the product xy is constant, and since x and y are the oblique coordinates of the point P, the asymptotes being the axis of reference, we have the equation of the hyperbola referred to the asymptotes as axis is xy equal to a constant. This identifies the curve with the hyperbola as defined and discussed in the works on analytic geometry. An elementary course in synthetic projective geometry. This book was written by Derek Norman Lehmer, Assistant Professor of Mathematics, University of California. It was published by Ginn and Company, Boston, 1917, and is now in the public domain. The text is available for free download at Project Gutenberg. Read by Jim Renholt. Programming and illustrations by Jim Renholt, 2020. Corrections and comments are appreciated. Thank you for listening.